So I'll speak briefly about hydrogeochemistry, devices we used, a couple of main issues that came up over the years, such as reliability and seasonal variation. We'll show a little bit of field results, and then we'll summarize. Everyone can hear me in the back, okay? So for hydrogeochemistry, I used Matt Laybourne's points. Not only are very good, but I also wholeheartedly agree with him. I think water is an excellent medium to look at area where there's no exposure, but also look at depth and at length of where you're working at, as well as understanding more the chemical or the geochemical signature of the area you're working at. For rapid hydrogeochemistry, if you're not used to working with water, just think of it as a handheld XRF for water. Like any real-time technology, the ability to acquire your data in real time at a fraction of a cost is a huge advantage to anyone who's working in the field and wants to get quick results. With rapid hydrochemistry, we can now get about 3/4 of a drinking water test suite, which is about halfway from environmental full suite to the enhanced cation suites that I noticed that the labs finally started offering the last roundup. And from this study, a lot of targets were, and the follow-ups were done while we're in the field within a day or two. It was done with small crews, very quick sampling, and observations. You don't need to filter with these devices. And the fact that you can do these fast and cheap, that means you can do that over and over again until you're really happy with the results or you get a better understanding of the area you're working at. So the devices we used, sensitive one, but this is a photometer we used in the last two studies. Reagents in the back over here, and the test suite's ready to go. The way that the photometer works is the reagents interact with the constituents in the test tubes to provide a certain concentration of color, and then the photometer translates it from a wavelength into a known concentration. The PDV we tried in the last study, it's right over here, and this is the testing cell right there with a whole bunch of tests ready to go. The laptop is not required for operations, but it makes it for easier operation, more precise one. So one of the things we looked a lot the last two studies is the photometer reliability. The first thing we did, we used certified color dyes from the manufacturer that has to come within a certain margin. There's 3 of them, yellow, red, and green, and yellow has the smallest wavelength over here and the highest scatter, and I don't really know why the scatter occur actually. I've been using this device since the fall of 2011, probably ran these a few hundred times, and this is the closest I've ever seen it come to the edge here. It's actually pretty impressive when you think about this kind of reliability. Another thing we looked at detail is repeatability. So what I noticed early on is some of the dyes were either shifting in color or there's suspended materials in the tubes and needed time to settle. So what we've done as part of normal procedure is we always run it 3 times. And if we get 3 identical results, then we log it. If we're not, we keep going until we get those, and then we average it. And then we analyzed the repeatability of that. And when you think about it, actually here, it's quite incredible results on these. Even the 2 high ones over here are still within the 30% margin that the EPA would like to see for these kind of repeatability tests. And the medium ones, it's when you deal with low detection limits or 1 or 2 ppbs, and then you get these changes and you statistically analyze it, you just get higher percentages. But again, these are also within the 10% that the environmental industry would even like to see this kind of repeatability. The last study we did also field duplicates repeatability, and again, very good percentages. There's a few high ones. For example, chloride here. We know we had some turbidity issues early on with some of our tests, which we resolved. And sometimes, like the 47 over here, is just you get only 1 test, and that's the percentage you get. That's what you get. Generally, with a photometer, the more tests you run at high concentration, the better the results are. I think it has something to do with that the photometer was really designed for an environmental industrial usage at higher concentration. And it was never really tested at the thousands of samples from natural water background tests that we ran at it. And yet we're still getting really good results over here. And another test we did is comparison to labs, the last 2 tests. Most of them come out very well. Some of them are above, some of them are below. We tried to address it with aluminum by using preservation. We got better results, but still not comparable. Again, I think it's something to do with what the photometer looks for. But it never really detracted from getting meaningful results for everything out there in the field. PDV is actually more straightforward. You get 2 calibration fluids from the manufacturer. The first one, you run your background test, and then you run your signature test. They have to be within 5% margin, which you can figure out from the notches on the left over here. This is cadmium, lead, copper test, and this is the arsenic test. I suspect some of the noise in the arsenic test over here is just because you're dealing with so much lower units. This test over here, these are microamperage over millivolts, and units here are half of this test. We had only a couple of repeatability or lab comparison ones, but again, the percentages were very good, and we got some nice results for the arsenics in the field as well. So one thing that's been raised to me a lot over the years, what about seasonal variation? Water is very sensitive. It's sensitive to weathering, pH changes, and my experience has been that, yes, there is some changes, but if there's something out there, you're probably going to see it. The biggest effect I've seen is maybe a reduced halo effect on some of the cation tests. But again, if there's something there, you'll probably see it. The principle that I use is that if you can go out and explore, maybe with the exception of winter, you can probably test for water as well and get something. But we looked at it in more detail in the last study. There's a lot of data to look through, but we decided 2 ways to look at it, per station and overall concentrations. And these are 2 opposite examples. Alumina over here, you can see very susceptible to weathering effect. In fact, some of the reverse peaks are quite obvious. And that could just be a daily effect, not necessarily a seasonal one. And for overall concentrations, generally what you expect is to see lower concentration because of dilution in the spring, and then higher concentration in the fall where dilution is supposed to be at its lowest and groundwater influx is highest. But in fact, alumina is actually doing the opposite, where higher concentration in June and lower concentration in August, where in the middle, probably an influx of high precipitation in September and early October was affecting it. And for magnesium, almost excellent correlation at every station, and hardly any changes at overall concentrations, which is actually, it was nice to see quite a few of the tests came out like that. One of the more interesting things we did in the last study is actually looking at daily variations. Until now, I used silica to see if there's any changes. Silica is very stable, and if there's any changes in it, then you know something's going on. But because of all the early precipitation we had, Ray had a great suggestion of why not just do totals in every station, and that's what we did. We looked at overall total figures every day, and we can see we get more what we expected with lower concentration in the spring, higher in August, but then the high precipitation in September and the influx in early October brought our data again. Well, silica is actually enhanced 5 times over here to show any differences. It's very stable across compared to all of them. And the nice thing about silica is actually you can normalize your data later on if you get a lot of changes like that. I think from now on, any study I'll be doing, this is a must, or any big studies like that you'll be doing, you probably need to do one of those. So a little bit of results from the first study we did at Mount Poison, which is about an hour northwest of Lillooet. This is dissolved copper from October. You can see nice correlation with the mineralized, non-mineralized area over here. And then another thing we did is a big comparison with stream sediment in both seasons. And you can tell there's nice correlation here in the mineralized area, nice dispersion pattern. And then for sulfate, August and October, you can tell nice correlation with the mineralized area and also a nice dispersion pattern for both seasons. And not a lot of changes between them. Notice also some of the correlation here with the stream sediment in the southeast. Sulfate is a very nice test to do in the field. It's very stable in water. It carries very long distances. And it's also an indicator for almost everything out there, for minerals, geothermal, oil and gas. It's used also a lot in the environmental industry. If you go out and do this type of survey and you do one test and one test only, sulfate is probably the one you should be doing. A little bit of results from NASCO from last year. NASCO is about an hour west of Cornell. Again, dissolved copper from October. Free is the photometer terminology. For the PDV, we did get some results around fishpot mineral showing over here. And then we did also total copper with a photometer, which is a really nice test to have in the field. The ability to see total copper in the field is a big deal. And we get nice correlation here on Bob. or a fishpot lake, and around a fishpot with the PDV, and also a whole bunch of showing in the south, which I'll talk about in the next slide as well. And again, sulfate August and October, nice correlation with fishpot, Bob over here, October at Fishpot Lake, and more correlation in the south. This time we're dealing with concentrations were about 1/10 from the previous study. We got 12, 14 high over here and single digits in October, and yet we're still seeing correlation with the known mineralized area in the south as well. So this is the last map from the last study. This is really what's putting it all together. For fishpot area, we got some copper and sulfate, as I mentioned, but the arsenic was really coming from the northwest. We're getting about 10 ppb over here, all the way down to 3 ppb, and that's actually a third stream order over there. It's about 10 kilometer, very stable over both seasons, and it's coming probably all the way from northwest over here. Drilling was down around here, and then there was some soil samples over here, and yet our really strong signature was coming from the northwest. Bob was a little bit more challenging. There was no drainage coming out of it. Drilling was done right over here and then 3 spots across, but our strong signature was actually coming from the southwest. We did a follow-up, and again, strong signature coming probably from this mountain range over here. And in the south, a whole slew of indicators lighting up this mountain range over here. Clisbaco is actually over here, and I don't recall seeing any Minfile ARIS reports around this big mountain range over here. Again, throughout the season, we're getting all these mineral indicators. Now, this slide is nice, going back to Matt's points, where not only we are correlating with the mineralized area, but we're also expanding on our knowledge of these areas, potentially showing us there's something much bigger than we originally thought. Not to mention the south, where it shows us a whole new area where publicly there might not have been anything written about it. So, as I mentioned, fast and cheap for rapid hydrogeochemistry. All of these were collected within days at much lower cost than lab cost. It's useful in the sense that we can, hydrogeochemistry is useful. You can go out and collect this data and get meaningful results. Reliability is there. I think at this point, the reliability of these devices, and we point, they're very good devices. From the last study, we can show we actually do these. We can go out and do these surveys and get meaningful results with follow-up. And last two ones are really big, but one thing about multipurpose is that if you go out and do these surveys, you can actually put out your initial environmental baseline as well. So if you get anything in those results, then you can later on show that you knew what was going on in that area as well. I'd love to go back and follow up, but I'm not sure where Trek is going from here. There's still a lot. That was really a small study. It was just repeating it over and over again. But there's still a lot to look over there. I'd love to go back around Clisbaco and have a look at more. But also, I think because it's so fast and cheap to do that, we can actually do a lot more comparison out there. And I know there's some interesting, people are interested in doing some soil leaching out there as well. For large surveys, I'm sure everyone will have their idea of where they want to go, but maybe Geoscience BC would like to hear more about where to do that. The nice thing about doing this fast and cheap right now is that not only we can provide these large data set very quickly and at lower cost, but also we can provide follow-ups while we're doing these surveys in the field, which I think is the next step in a service we can provide to the community that is actually using this data set. And for devices, it'd be nice to do a little bit more testing with newer devices, or maybe tweak some of the issues we had. But these devices are designed and manufactured for lab use, so they should actually be pretty good. You can buy them off the shelf and use them. There's a learning curve associated with it and the methodology, but I think it's more of a nice to have than a must have. But it'll be nice to get to use more reagents in the future. And of course, thank you for Geoscience BC for all the funding, and NASCO band for helping the last one. Special thanks for my co-authors and all the field people. And one thing I forgot to say is Craig and Peter Bradshaw for early encouragement and support. Thank you.